The deep story of where research into dark matter and dark energy is going has only increased in importance with recent discoveries of hints, separate from the effects we already knew about, that both dark matter and dark energy actually do exist, and in fact may be interacting with each other and may comprise some kind of complex hidden world set within the universe that may be significantly more complicated than simply the existence of another neutrino-type non-interactive particle. Indeed, it may actually be what's governing the universe and is responsible for some of the biggest underlying mysteries of astrophysics and cosmology today. One idea here involves a strange, relatively new idea known as dark radiation. This comes from a discovery in 2024 by the DESI instrument in Arizona that produced a 3D map of the universe that hinted that our ideas about dark energy, the initial ones, may be a bit erroneous. The strange energy behind the observed acceleration of the expansion of the universe. You still need some kind of energy to drive the accelerated expansion, or else it wouldn't be happening. You don't go anywhere in a car without fuel in the tank, but the mystery deepens. This actually runs against the standard model of cosmology, in which the standard model was predicting that dark energy and dark matter do not interact. But this may be wrong, according to the 2024 work. If energy can flow from dark matter to dark energy, as this implicates, one essentially converting to the other, that could explain why the expansion is accelerating, in that dark matter is slowly converting to dark energy, changing the balance in dark energy's favor, causing the increased expansion because there is more available dark energy to do it as the universe ages. Consequently, dark matter would be reduced as dark energy increased. This has an advantage, even though it's unclear how it actually happens. It's unknown what is converting matter to energy here. The origin of this idea is known as dark fluid that links the two. That advantage is that it might help to resolve the Hubble tension, the apparent disparity which shows a lack of agreement between the two main ways we measure the expansion of the universe. They don't agree, despite being physically valid ways to do it. How it changes is this. So one way to measure it is to look at the afterglow of the Big Bang, the cosmic microwave background radiation. This gives one number. The other way is to look at local galaxies, and you should get the same answer, but you don't. The local one is slightly higher in that it requires an adjustment to the CMB measurement due to a new factor, and it then may fall into line, which it might since the local galaxy measurement is in question by recent evidence, meaning it may be very slightly lower than previously thought. But it is still unclear how the interaction between dark matter and dark energy is happening. But there is another idea here, and it's dark radiation. So normal photon radiation is well understood, but it may have a dark counterpart, the dark photon, that cannot be seen and doesn't interact with regular matter. This could account for the 2024 observations by DESI, in that any other alternative hypothesis isn't particularly simple, and causes proto-ideas of new physics. Dark photons do not require that. Only more data will tell there, but it does evoke ideas of another area regarding interactions between dark energy and dark matter. Dark matter is basically still a wide open field. If you look at what we actually call dark matter, it's usually characterized as some kind of weakly interacting massive particle or WIMP, like the neutrino. It's just another type of that kind of particle. On its face, it's a simple answer, and the most likely seeming one. But there are many others, such as dark matter being a strange population of primordial black holes, still existing from the early days of the universe, asserting their collective mass that we can't see. In which case, that's not dark matter per se. That's just black holes exerting their mass that formed from normal matter. But if it actually is a particle, the question then becomes how complicated is that world? Is it one single type of particle or many? Our own matter says it's not likely to be one. We have many types of matter. So are there dark atoms, dark objects, dark asteroids, dark forces separate from those of matter, or even life? We don't know. It's all hypothetical and speculative. But hypothesis and speculation is how you know where to start looking for evidence. So it's a necessary step. Otherwise, you're just stumbling around blindly, hoping to run into something by accident. Now, there are skeptics of dark matter, often citing theories like MOND. But the problem is these theories do not eliminate the need for dark matter. MOND doesn't. You still need it, just less of it. But these hypotheses often do not explain all the evidence pointing towards dark matter. So you have the famous galaxy rotation evidence. They have more gravity acting on them than their visible matter can produce. But you also have a fingerprint in the cosmic microwave background radiation that also points to exactly the same thing, two separate lines of evidence. There's also the large-scale structure of the universe providing a third. But what seems clear is that whatever dark matter is, it didn't just appear, but was something that emerged naturally from the conditions of the early universe. One idea derives from QCD theory or quantum chromodynamics in physics. This theory describes how quarks bind together inside of protons, and accordingly neutrons through the strong nuclear force. That ultimately makes up hadrons, which are integral to normal matter. For dark matter, there may be a dark version of QCD theory. This takes a certain step, and defines dark quarks, dark gluons, and so on. This steps beyond what we know about dark matter, but it mirrors normal matter. Those would form dark baryons. And long story short, this opens up the way for things in the dark matter universe to get massive enough to collapse into stable black holes, albeit probably very small, exceedingly so, but they would act like black holes as we know them otherwise. When I say very small, I mean very, very small. These things would only be a bit larger than the Planck mass, but if there were enough of them, a lot of them, then they could account for dark matter as we see it. Since they only interact with gravity, they would otherwise be invisible to any detectors we have or can conceive of. To find something of that size at such a small scale is not realistically going to happen anytime soon. Gravity is far too weak at those scales. A problem that plagues any questions about gravity at the subatomic level. It's only barely there. But there is a way it could be testable, at least eventually. Another option for dark matter is that it's actually being produced by the universe's expanding cosmic horizon. So a horizon in physics ultimately is just a barrier you can't see past. So an event horizon of a black hole is just the point where you can't see what's going on inside it. The universe also has a horizon, a point you can't see past. In the early universe, it went through a period of accelerated expansion known as inflation. But this idea proposes that after that, there was still a rapid expansion period going on that might have created new particles. A recent paper showed that this could result in large masses of dark matter to result from that mechanism, depending on things like temperature and how long that period lasted. There are a lot of unknowns here ultimately, but they are testable and may offer alternative paths to the nature of dark matter being a bit more complex than just a new type of particle that doesn't interact. It might be a lot of new types of particles that do not interact with anything other than through gravity. Thus, this approach could be termed dark radiation. The takeaway from these ideas so far is that dark matter and dark energy may be more complicated, perhaps far more complicated than was initially thought. But then there is the related dark flow, yet another facet of the question. This comes from unexplained measurements of velocity in galaxy clusters, something that already shows evidence of dark matter. Indeed, it was the first evidence of dark matter discovered in the 1930s by Fritz Zwicky. The idea is that the motion of galaxy clusters in relation to the cosmic microwave background should be random in all directions. Evidence from the WMAP instrument showed this to not completely be the case. The idea here is that the differences in motion are a remnant of parts of the universe beyond the cosmic horizon that are no longer visible, but influenced the universe very early on, actually before the inflation period. But the evidence here is contradictory. Indeed, dark flow was determined in one case to be flowing in the direction of Hydra and Centaurus in the night sky. In other words, towards the mysterious Great Attractor. Something is pulling galaxies towards it in that area. But the area we would need to see is blocked by the plane of the Milky Way. Ultimately, it was thought that the Great Attractor was ultimately caused by the Norma supercluster, about 250 million light-years away. Nevertheless, the controversy over dark flow continues because there are discrepancies with that interpretation. These range all over the board, from a sibling universe affecting our own, to regions of spacetime where the laws of physics are different, and so on, of which there is no proof for. Others claim that the data we have, which is extensive on galaxy clusters, shows an unmistakable trend of flow that can't be explained here without some new factor. Or it may simply be that the phenomena of dark energy and dark matter are still too unconstrained in the face of not enough of a data set that allows for a panoply of hypotheses, most of which will turn out incorrect. The real trick is in determining, as better data comes in and constrains it, which one is right, whether dark energy and dark matter are closely related or not really, and so on. The simple answer is that it's cutting-edge physics, and no one really knows the deep answers, other than how the universe behaves suggests their existence. Only time will tell if we can constrain that data down further, or if it all will forever be a mystery because of a lack of ability to actually collect the data needed to find the answer. Thanks for listening. I'm futurist and science fiction author John Michael Godier, currently eyeing the various dark theories of the universe suspiciously. The only reason we use the term dark is because we can't see something directly, only indirectly through effects. Well, if that isn't a way for the universe to be hiding something, I don't know what is. That's what the universe does. It hides things. From your missing sock to the bulk of the matter and energy in the universe. I'll go on record. The universe is questionable. But science always knew that, which is why they ask questions. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.